about the bias-variance trade-off for square error loss function and optimal penalization. Consider a population of just 6 observations. So these are the numbers from 1 to 6. Their average or expected value of mu is equal to 3.5. So the task here is given a training set, for example T1, which is a random sample from the population, to estimate mu. The estimate is denoted as mu head 1. So for example, we have training set 1 are the numbers that we have drawn 2, 2 and 6. Notice that in the training set numbers can be repeated because we have random draws from the population. Otherwise they will not be random. So we decide here just to have a model which is the mu head is the average in the training set, which happens to be 10 over 3. And this is unbiased estimator for mu, by the way. The average in the training set is unbiased. The question is this a good estimator, or we can find a better one? And it will turn out that with optimal penalization we can. So we design an experiment. So to test if we estimate mu with a good model, we run the following experiments. We generate t training sets of size 3. So instead of having 1, we don't know if we have started with T1, maybe we have started with another training set. So we have to say over all these possible training sets, what will be our expected loss? This is what we would like to minimize. And from each model, we estimate the mu. We predict the test set, which will be very huge. It's actually the population itself, but we can draw from it infinitely many examples, although there are just 6 observations. So we just draw these 6 many times. So we start with training set 1, which is yj, yk, yl. We compute mu. This could be just the average, could be another model, but it's a running example. Just the average in the training set. We have a test set, which is the future examples. So we assume that the training set and the test set are independent. So mu head 1 and all the y's are independent. We can then make a second training set with another 3 observations. We compute mu head 2 from it. Then we test it out of sample. Again on the whole population. We have the square error loss, therefore we compute the error as the square difference of mu head and y. And for training set t, we have the same, t goes to infinity. We have another expected mu head minus y from training set t. And this is actually called from each training set the expected prediction error, the expected prediction square error. We have this from all training sets. And then we see on average what happens. On average, the loss is what we should minimize. It's called expected prediction square error over all training sets. In here I have shown explicitly the summation that goes into expected sum, and we can say that since the y's are drawn at random, the summation, so the average over y is the expected value of y, and the same goes for the training sets. You can say the summation 1 over t and the sum t from 1 to t of the expected prediction squared error loss for all the training sets is just the expected over training sets, expected prediction training error. So just the average. Then what we do is to introduce alpha. So we have an estimate mu head, maybe it was the unbiased estimate, and then we multiply this by alpha, and we want to minimize the expected over training set, expected precision squared error with respect to alpha. Here follows the derivation, very explicit. At some point we have to assume that mu hat and y test are independent, which means we compute mu from training set and y's come from the test set in order to see what is the expected test error, not the training error. And then after we develop this, it happens that alpha optimal will be equal to mu times expected value of mu hat divided by expected value of mu hat squared plus variance of mu hat. And if mu hat was unbiased, this reduces to mu hat squared divided by mu hat squared plus variance of mu hat, which means that alpha is between 0 and 1 of the optimal alpha when we penalize an unbiased estimator. Biased estimator meant that the expected value over the training sets of mu hat is equal to mu, which is occurs, for example, when mu hat is the average in the training set. And this is a very powerful derivation which says that in theory we should always penalize an unbiased estimator with alpha, but this alpha is a theoretical, we cannot compute it in practice.